Hello. It's very nice to meet you, Markus, in our studio and our conference. Thank you for coming. Say
Yeah, it
something.
wasn't far, right? My bedroom is over there.
Yes. Yes. Let me introduce you, Markus. Markus is a software engineer at Microsoft Research, and we will certainly will ask him how it is to work in the Microsoft Research. And yes, his mission is to share the knowledge about TLA Plus and spec-driven development with you and everyone in the world. Markus, tell us about yourself, please, how it is to work in Microsoft Research, what it is interesting there, and how you end up with the TLA Plus.
Oh, uh, my biography, I guess, is interesting. Started as a student at INRIA, working for Lamport, and then gradually, moved on to eventually end up at Microsoft Research. And Microsoft Research is great. A lot of great colleagues, brilliant colleagues, highly inspiring colleagues. It's awesome to be at Microsoft Research and to be allowed to contribute to the work that's done there.
Okay, by the way, another interesting question that I have for you. I saw that you picked a termination detection algorithm for your workshop today, and specifically Safra's EWD998. I wanted to ask you what it is special about it, why you picked this specific algorithm for our practice today.
So the thing with TLA Plus is it's a modeling language, and the ideal TLA Plus workshop would show how to design something truly novel, right?
Yes.
To show the powers of modeling and of the language. But this has a lot of pitfalls, right? If something, it might not work with a new thing. So I had to choose something that that actually works. And we could have gone with Paxos, which is, I guess, the example for TLA Plus. But it's too complex for a workshop. Then you not only have to learn TLA Plus, but also to deeply understand Paxos. Most here would probably understand Paxos, but not all of them. So I had to settle for something simpler. I could have gone with a toy example, but that wouldn't really show the powers of TLA Plus. So I settled for the middle ground. And I suppose that this algorithm by Safra is old enough that nobody remembers it anymore, but it's still interesting enough to be studied with TLA Plus.
Okay, thank you. When I was, I guess I know if our viewers know, there is a also very detailed and good introduction into TLA Plus by Leslie Lamport. And as far as I remember, he describes there in the implementation of the two-phase commit, which is also a very nice thing. But what I wanted to ask you before we proceed finally to the workshop, how do you think can be the TLA Plus be used by the guys who are not familiar with the math?
Well, I guess this is what we're here for, to learn a little bit of the math. The somewhat longer answer is, before we all learned programming, we didn't know a thing about programming, about the syntax of programming, about the semantics of programs and of programming. Still, we managed to learn it, right? So now we learned something new. My hope is for us all here to learn something new, a new tool for our engineering tool belt that uses a little bit more math or looks more mathy compared to programming, but which is fundamentally, internally, a lot simpler than programming, because it's just math.
Yeah. Okay. Once again, Markus, thank you for coming, and let's start our training.
Awesome. Great. Okay. I guess we are past the.
By the way, Markus, wait a second. I'm sorry.
Okay.
Shall we ask our viewers to join the Zoom session or something
Exactly.
else?
Exactly.
Yeah. Okay.
This is supposed to be interactive, and I guess this takes me to the second slide.
Yes. Please, everyone, find a link to join the interactive training session to Zoom right now in the bottom of your video player. Please join the session. And Markus.
Yeah, I see the first people joining.
Yeah.
Hi there.
Markus,
okay,
please continue.
Thanks. So, as we've already started, let's quickly talk about the layout of the TLA Plus workshop, TLA Plus in action, pun intended. So I believe that you will best learn if it's interactive, if it's hands-on. That's why I want to write a TLA Plus spec with you together, not just looking at the language, but also to meet its tools. So what the tool set, the ecosystem of TLA Plus has to offer to make you better at writing specs. You've already all started to join the Zoom meeting. That's great, because I want this to be a discussion. Like, we could pretend as if this is a code walkthrough that you do with your colleagues at work. We've been tasked with solving a problem. I happen to know a little bit more about the problem. I'm going to teach you through Zoom. It's fine if you unmute yourself, ask questions. Let's try to keep an etiquette here so that there's not too much background noise. But please feel free to ask questions during the talk. The material happens to be a Git repository where each commit represents a new concept of TLA Plus, or this termination detection algorithm that we're going to study with TLA Plus. And the advantages, from my perspective, that should you miss a step in the workshop, in the tutorial, you can just skip to the next Git commit, and then you have a known good baseline. This is all inspired, the structure is inspired by talk of mine. Weeks of debugging can save you hours of TLA Plus, which is a little bit more fast-paced compared to this workshop here, and specifically, it doesn't introduce the syntax. So this workshop here, termination detection, is similar to weeks of debugging saves you hours of TLA Plus, except it also teaches you the syntax and the semantics of TLA Plus, and does not only show you how the tools work and the powers of TLA Plus. It's really meant to be 4 sessions, 1.25 hours each, spread over 2 days. So we have in total approximately 5 hours. That's obviously not enough to fully learn TLA Plus. That's unrealistic. But still, I want to cover all the important parts of TLA Plus, because I want you to understand how they fit together, how the tools interact, how they collaborate the tools, how the language concepts also work together and build something that, the closer you look, feels more consistent. If you are really deeply interested in the theory of TLA Plus, well then Leslie Lamport wrote this book, Specifying Systems. 300 pages with all the content, all the theory you want. And also Ron Pressler wrote this very beautiful blog post series, TLA Plus in Practice and Theory, that you can find online. And by the way, here on the right, you can see this QR code and this link, etc.ch, and so on, CIM6. There's a survey with a few formulas. It's not a test. This is all not a test. We're here for the learning. There's no exam at the end. There is no grading. But please, for me, answer these questions on the survey now, so that at the end of the slide deck here, which is just 8 slides long, I get a sense of your background and know how fast I can go in the workshop. Everybody knows the basics. We can just skip a few of the initial steps. But if the survey turns out that everybody wants to start at the beginning, that's fine. Okay, a little bit more about me. Most of it has been covered already. I'm a software engineer, no mathematician. I learned TLA Plus by working on its tools, been doing so for a decade now. Don't learn TLA Plus through its tools, by working on its tools. That's a terrible way to learn TLA+. Rather, model something real in TLA+, or attend a workshop. That's a good idea to learn TLA+. I wrote many specs, examples, but also I eat my own dog food. So I wrote specs for the TLA+ tools that model some internal part of, for example, the TLC model checker. I guess some of you might have seen yesterday's talk by Jack Van Lightly comparing TLA+ to Maelstrom. So you probably know this high-level perspective on TLA+ already. For those who don't, TLA+ is not programming. It's not another programming language that claims to be better than your other programming languages. That's not it. TLA+ is a specification language that sits between your document, your prose document, and your implementation. It tries to close this gap between prose and code. Code is great for a machine to execute or to be turned into something that a machine can execute efficiently. Prose is great for a human to read, but it's highly ambiguous, right? Writing very good prose is pretty hard. And also you cannot verify your prose. And this is where TLA+ comes into the picture. So you have a third language that's highly precise. It uses math, so it's also highly expressive. And it has the added benefit that you can verify your documentation in the sense. But it won't give you an implementation. You cannot press a button and at the end there's an implementation coming out of it. That's not it. That's still for you to do. But it's what might look as a problem initially turns out not to be such a big problem. It's really designing a huge system, a complex system. We need all the tools we can get, and TLA+ is a very important one from my perspective that should be part of your tool belt. Okay. By the way, let's quickly go back. It all goes back to Lamport, the creator of TLA+. You all know him, right? He doesn't need an introduction, Turing Award winner. He designed many distributed and concurrent systems, and TLA+ is what he thinks is the right tool to build those kinds of systems, those kinds of reactive systems. Okay, can this work in practice? Is this practical, or is this just a toy thing or a research idea from the ivory tower that hasn't been applied? Well, TLA+ now goes back 20 years approximately, and initially it was used by hardware engineers, and then gradually the software engineers also started to pick up. And perhaps the most popular case study or application of TLA+ was eventually documented and written about in a CACM article, a longer paper by a group of Amazon engineers when they, around 2013, 2014, designed parts of AWS. So they were working on DynamoDB, and you probably all know what DynamoDB is, this global database with strong consistency guarantees. And the engineers started with the traditional techniques, write design docs, have design discussions in front of a whiteboard, perhaps write a handwritten white paper proof, pen and paper proof. And then once they had a good feeling, they decided to do a prototype and test the prototype. Excessive testing, fault injecting testing, unit testing, functional testing, through all the testing in it, they could. And things worked, seemed to work. And then they had the feeling, you're okay. So for the scale that we as AWS envision, this might not be good enough. So let's see what the formal methods have in stock. And they looked at a bunch of formal methods. They eventually liked TLA+ best. So they specified this design of DynamoDB in TLA+ again. And this model checker found a very subtle bug after 35 steps of the execution of the computation going on in DynamoDB. At the spec level, 35 steps at the spec level probably translates into an order of magnitude or 2 orders of magnitude more steps at the machine level, where you would execute the code. So it's very difficult would have been very difficult to reproduce with testing, and it's already super difficult for a human to reason about. I mean, we can all handle like 7 or so variables. Here we're talking about 35 steps. And then in the CACM paper, they conclude that if they would have started with TLA plus instead of traditional proof writing, they would have likely improved time to market, they would have been done faster, and would have achieved greater confidence in the system's correctness. So this is what the engineers around Chris Newcomb wrote in CACM and in the longer article. So it works in practice. Real projects, real teams get mileage out of TLA plus. Okay, great. So we hear you, please mute yourself. Okay, that's a chat that's not directed at me. Let's switch over to the workshop material. As I said, it's a Git repository. It exists on GitHub, github.com/lemmy/ewd998. I have a bigger link over here. So here's the highlighted link, and I hope you can all see it. I can even make it bigger. github.com/lemmy/ewd998. You can also see the agenda here. Part A is what we hopefully cover today. If not, that's fine. We're here for the learn. You don't have to fork this repository, but you can simply click this button on the main page of the repository that says try in Gitpod. And this opens a browser-based IDE for you. So it will take a while, take a few minutes. Let's look at the results. Okay, 70 participants, that's great. And I guess most attended yesterday's talk, Jack's talk. That's great. Thanks, Jack, for bringing the people here. And you all know implication. That's also awesome. And the rest we will cover today. Great. So while your machine and my machine is doing the technical setup here, this is spinning up the TLA Plus IDE in the browser with all the tools pre-installed, the model checker, 2 model checkers, a proof assistant, and so on. We can focus on something more interesting, which is the actual problem description, the problem we're trying to solve today. And I'm going to switch to my other stack of cards here. README. Let's make this faster and make this bigger. Because as we discussed in the introduction, we want to solve termination detection in a ring of computers. So we assume we have a bunch of computers who happen to be organized in a ring, meaning each node knows its successor node. And we want to find out at the global level whether or not this system has terminated. And each node carries out an individual computation. That's depicted here in this animation, that a square is a node that's terminated and the circle is a node that's active. And we can design, if we think about this, take a walk, think about this for a while, we can come up with a super simple protocol to handle this kind of termination detection in a ring. Assuming we have a leader, we don't have to do a leader election, we have this ring, we can just send something like a token around the ring and wait for the token to arrive back at the initiator. And if a node that's still active holds onto the token as long as it's computing, well then by the time the token gets back to the initiator knows that global termination has occurred. It's obviously way too simple to be useful, right? Because this is embarrassingly parallel. Nodes don't communicate at all. There is no reactivation. This is not a useful model of our system, because a more realistic system is obviously one where there's communication between the nodes. And suddenly our super simple algorithm from before doesn't work anymore, right? Initiator still sends a token around the ring, but now it might happen that a node who hasn't received the token yet reactivates a node that already passed the token along. Yeah, we can see this in this animation. Token number 2 will eventually send a message to the token number 8 or token number 7, I believe, after token number 8 or 7 passed on the token. And then the initiator would incorrectly assume the termination, global termination has occurred. So we have to update, we have to pimp our protocol by saying that nodes maintain the state, whether or not they've sent a message. And this marks the node black. We just arbitrarily define this to be black. So once the node is black, it maintains, it keeps this information. And when it gets the token, the node will taint its color onto the token. So the node, the initiator, eventually gets a token back that's either black or white. If it's black, the initiator knows, oh yeah, termination has not occurred, because the token is black. Some node sent a message that reactivated some node. So instead of just doing one round, the initiator now has to do multiple rounds over and over and over again until the initiator gets this token back and it's white. So this works, this protocol works, and it's due to EWD 840, also a writing of Dijkstra, but it has one simplification that we don't want to live with, because it requires messages to be atomic. Message sending is atomic with this protocol. The moment a message is sent, it's already arrived at its destination. And this obviously won't work in a distributed system with arbitrary message delivery times. So we have to, yet again, extend our algorithm and make it handle the case where we have asynchronous message delivery. And this is then the EWD 998 here, where a dashed arrow shows that a message is in flight, and a solid arrow means that the message arrives in the next state. We're still going to use our previous ideas of a token and coloring nodes black and white, but extend the overall thing with the idea of counting the in-flight messages. And then nodes not only taint the token, but they are also going to add the number of in-flight messages, of their local in-flight messages, to the token. And the initiator at the end can do the final tally and see if the aggregated result translates to 0 messages in flight. Now we have a local counter at each node that gets incremented when the node sends a message. It gets decremented when the node receives a message. And globally, obviously, the aggregated result, if it's 0, there are no messages in flight anymore. And the initiator, once again, sends this around, sends the token around until it gets it back as white, and with a tally that accumulates to 0. Okay, and now the question for you that you should answer for yourself. This seems simplish, I guess. It's certainly not a toy example, I would say. How long would you say does it take to implement this in your most favorite programming language? And then also get strong assurances that this works. Perhaps in a couple of days, maybe a week or so. I mean, obviously you would be working from this existing paper, and the paper EWD 998 confirms that this already works. But if you would have come up with this algorithm yourself and you would now start implementing it, I guess you would learn many more things along the lines, working on the implementation, that would perhaps, if you would have known them in advance, would have allowed you to simplify some things. And this really is where TLA Plus comes into play, where we can specify this algorithm before we implement it and see if this basic idea of sending a token around the ring, doing a tally on the token, tainting the token if a message has been sent or not, works and always guarantees to detect termination if termination and only if termination occurred. Yeah, this is really the goal. So, are there questions so far? Either in the chat or, so there are no questions in the chat. Feel free to type into the chat. I have the chat open, but you can also talk to me if you want. Okay, if there are no questions, when the, okay, so the question is, can you please say when we will color the node black? The node will be colored black when it sends a message. Like in the previous, in the simplified and in the simpler version of it, a node gets colored black if it sends a message. But as you can already see, right, this is also the point here I'm trying to make. This prose, this informal description of the algorithm is highly ambiguous, right? We see a few examples here. We see a circle going around a ring of nodes. And there's so many corner cases we can already see, already can think of. We really need something precise. This informal description, that's not good enough. And even if I would sit down and write it down in a work document, it would be way too imprecise, informal for you to make sense of. So let's try and write a TLA plus spec that is ultimately precise and exactly lays out what the protocol is. Okay, somebody raised the hand. I don't know what to do, how to acknowledge it. Please just type into the chat or unmute yourself if you have a question. Okay, I guess it's been answered. So let's switch over to the TLA plus spec. Okay, so I've already started with a skeleton of a TLA plus spec. And before we really jump in and start writing the math, I want to make one thing clear. TLA Plus has the concept of refinement. It doesn't mean anything to you yet. That's fine. But it can be translated into divide and conquer. So you can simplify things by applying divide and conquer. This is what we are going to do from the beginning. This might feel like overhead, and also because this is a simpler algorithm, it might feel like overhead. But if you design more complex systems, you want to divide and conquer. If you look at Lamport's Paxos specification, it actually consists of 3 different specifications. One defines what it means for nodes to achieve consensus. It's a super simple specification, and it's just a few dozen lines long. Then there's a slightly more complex specification that discusses how voting achieves consensus. And then there's a 3rd specification, Paxos, that defines how voting is achieved under message loss. Yeah, and this is the same technique we're going to use here. We're going to write a specification initially that just checks if counting messages in a ring will allow us to detect termination. This is so simple, obviously, yeah, this will work, right? We all know that this will work, but we are also here to learn TLA plus, and it's, I guess, the nice trade-off between writing a super simple specification and learn TLA plus. You can already learn a lot about TLA plus itself, writing the specification. It's a simpler problem, and we're going to reuse it later and make use of this specification later to show how TLA plus, how the concept of refinement in TLA plus is useful. So you don't see the file in Gitpod, that's fine. So if you open a terminal in Gitpod, new terminal, I created the N and P command. So the N command takes you to the next commit and resets the workspace. And the P command takes you to the previous commit. So if you type P, you go to the previous command, and if you type next, you go to the next command, commit. And I moved to commit to some commit version 02A04. So I skipped a few commits at the beginning, which are super simple and just show you how to set up a file and stuff. There are, by the way, there are to-dos in the material. So let me go back. So if you want to follow up with the material later, in your own time offline, there are exercises in each commit. So here, for example, is an exercise for the basic set theory underpinning TLA plus that you can also try out in the REPL in your own time. Okay, so let's move forward again and introduce the boilerplate of a TLA plus specification. Okay, as I say, so the question is how to open Gitpod. That happens if you click this try in Gitpod a button on the README on GitHub. But I would say if you by now don't have Gitpod open in front of yourself, on your computer, that's fine. Pay attention in this session, and then we can work on this in the break, during the break, to get you set up with the environment. Just pay attention, follow along, look at watch what I'm doing. I will do the same here, and then we can fix any environment issues later. Okay, but now let's really jump in and learn TLA plus. As I said, a simplified specification, async termination detection, where we're going to model how we count messages. We're going to leave out this token for now. So in this first version of the specification, the token is gone. It's too complex for us. We will start with something simpler, validate that this simpler thing works before we move on to the next part with the token, combining it with message counting. So the first thing we do here in the module is we extend some other module. TLA plus comes with a few standard modules, really a handful, just a handful. Naturals gives us a few useful operators on the natural numbers. And it's really just concatenating the naturals module on top of our own module here. So all the definitions in the naturals module are available here in async termination detection. And then the interesting thing is here this constant n. So that means we have some n that's not going to change throughout the computation. What is it representing? Well, the n, I've defined it so that the n will model the number of nodes in our system. I think in the animation, it will have 8 nodes or so. So this will eventually hold the value 8. If we want to instantiate our specification for 8 nodes. But really, we want to write a specification for any finite number of nodes, right? Not for an infinite number of nodes, because then termination detection will take forever, but for a finite number, any finite number of nodes. But because TLA plus is untyped, and not because we hate types, but because we think that types are not required in small specifications that only span a few files and a few hundred lines long, TLA plus is untyped, and this flexibility that we gain from it, we make up for in terms of correctness by stating, for example, assumptions. So we assume of this n that it's in this natural here, in this NAT net, without 0. This looks a little bit strange. What is this? This is a little bit of set theory, and I'm pretty sure that you will know what it means if, I guess I have to always open this twice. If we look at the pretty printed version of it, because now you might remember your high school math basic set theory that says n is in the natural numbers with a 0 removed, right? It's a positive natural number, net plus in some other notation. And that's just it, right? The in symbol here is pretty printed to look this, to be depicted by this beautiful symbol here. We have the nut, which is just a set, minus the 0th element here. Okay, so we now know that n is a natural number. It's fixed throughout the computation. It's constant, doesn't change. You know constances from programming languages. And then we come up with a first definition, because really now, if you think about it, how would you design this ring of node in a program? In a real world program, you would probably have computers, right, representing the nodes. And then when you want to test them, you would have to run all these computers in a data center, and they send messages around. Here we will use the most abstract way I could come up with to represent these nodes, which is just a sequence of numbers. And it has the advantage that it already has a total order, right? I posed the assumption that a node knows its neighbor. This is easy with the natural numbers because it's just my number minus 1. And this is what we are going to use as our mental model for the ring of nodes that carry out the distributed computation. Okay, and then we have a bunch of variables. Variables are interesting because they can change over time, right? Again, there are no types, so we can just write variables, and then we list our variables. We here have 2 variables, active and pending. And in a minute, we will discuss how to formally specify the value of active and pending. Right now, active is going to track the individual active state and inactive state of the nodes. In a programming language, you would probably use an array for this, and then each array cell represents one node, and the value is some Boolean. And pending, similarly, is going to be an array, and it's going to track the pending messages at each node. Need a little bit of another definition here, vars, which is a sequence. More on it later, right? We can skip this for now and don't need it. What's really the interesting part now is to define how this protocol works. What are the steps, the transitions the system can take? And these things are called actions in TLA class. And I've already gave you a little bit of boilerplate of how I want to call these actions. So we have a terminate action that takes an I, could have also been N here, the symbol. This is the ID, the number of the node that terminates. And what it does is, this node simply decides, okay, I'm done with my computation. Whatever my computation was, I'm done with it. So what we will soon specify here is that we flip this active state for this particular node from being true to false. Pretty straightforward. Then we have a send message action. This takes an I and a J because it sends a message from some node I to some other node J. That's the other action, this second action that our system can do. And then the third action is the wake up. It's the receive of the message by some node I. And these define all the 3 messages we have here. What does keyword unchanged mean? Good question. So right now, I just came up with a little bit of boilerplate and it doesn't make much sense yet. Unchanged vars means that the values of the variables here, of our 2 variables, active and pending here, do not change if this action gets executed. It doesn't really get executed, but if this action is taken, the variables active and pending don't change. With this specification here, nothing happens, right? The variables don't change. And we'll soon remove the unchanged to do something more useful. But in TLA+, it's important to know that each action defines what happens to all the variables, not just to the variables that are changed in an action, but really to all the variables, even the ones that are unchanged. In a program, you can just manipulate individual variables, and the other variables implicitly remain unchanged. Or not if you have some side effect, unintended side effect that might write to your variable that you thought wouldn't change, but it could just change concurrently. But in TLA+, because this is math and math is precise, we state that the other variables, even though we don't really touch them, they don't change. And later on, we will also see why it makes sense to say the variables don't change. Okay. And then we will know what our system can do. It can terminate, it can send a message, it can wake up the global system. We also have to define how the system looks initially. And this is what we will do up here in the initial predicate. And initially, probably all nodes are active and there are 0 messages pending, perhaps. So let's move to the next commit. Because this is what I now wrote down without writing it down because I don't want to mistype all the time. So here's the initial predicate that defines the value of active. And the value of active is defined to be what might look like an array. And right now, the mental model of an array is fine. It even so happens that our nodes, the definition of nodes at the top was 0 ... n-1. Well, what does this stand for? 0 ... n-1 is just the set of natural numbers from 0 to n-1, which also happens to be usually the indices of an array, right? So here we now have a function n to node, and we can, let me quickly do a minor modification to the spec here, so we can evaluate this expression without defining the n here. So now I just define n to be 4, and then I can evaluate this expression, and we can see, yep, this is really looks like an array, right? 0 is mapped to true, 1 is mapped to true, 2 is mapped to true, and 3 is mapped to true. So all nodes, conceptually, all nodes are active at the beginning in the initial state. The math, really, what's going on here is that we have a function, and the function has a domain and a codomain. Some might wonder, what about partial function? What about total functions? In TLA+, there are no types, so it really doesn't matter much to talk about partial and total functions. We just have a function that maps some domain. In this case, it's a set of nodes to some value, and the value here is true. And we can do the same for the pending variable, right? Except that we won't map the nodes to true, but to 0. Because as I said, initially, there are 0 pending messages for every node. And since TLA+ is not programming, these two statements are not separated by perhaps the semicolon. What we do instead is we really write a formula that evaluates to true or false. We don't know yet what gets evaluated and how this would look like in practice, but we have to combine our subformulas with some logical Boolean connectors. This here is the end. In programming, it would be similar to, but not identical or equivalent to ampersand, ampersand. In programming, sorry, you might have written this one. But usually in programming, we just write this in if constructs, if statements. Here we just write a formula and we say this and this. This has to be true and this has to be true. Active equals so-and-so has to be true, pending equals so-and-so has to be true. Well, both of them are true, so this formula will be true. And it's convention, it has a little bit of syntactic sugar, this TLA plus, that says you can also write the end in the front and then create these lists here. This is just really equivalent to what I wrote before with the and in between. Now it's moved to the top. And if you write long lists of it, of conjunct lists, then, and here would be some other statements, yada, 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 then we think this is more readable than using parentheses or so. Except now indentation matters, like in Python, indentation matters. And you have to pay attention to the indentation. Anyway, we've now defined what the initial states of our system are, right? And there happens to be just one initial state. All nodes are active, 0 messages are pending. And we've already learned the first little bit of TLA plus, the plus in TLA plus. We have functions, and a function has a domain and a codomain. By the way, this n in node here, the n doesn't appear over here, but it could appear over here. So if we would want to define a function, and whoops, where is it? Here, damn it. This would then multiply the n coming from the left-hand side by 42, and this would define the value of the right-hand side for this n, right? So this n in can be thought of as an iterator over the elements of node. But we don't need it here because regardless of the n, we will assign it to true. Awesome. Next step. So it continues down here. So the terminate action. And some work been done in the terminate action. So when can the system, can a node terminate? This is the individual node terminating now. So when can this node terminate? Well, it can only terminate if it's active. Doing some kind of computation, now it's done, and it becomes inactive. That, as I said, flips the value of active, of the ith value of active from true to false. It can do so if this is true. So this is equivalent to writing true, just a little more concise. And now really comes the interesting part in this action here, which is the prime symbol. It's this tiny prime that I suffix this active I with. And what does it do? It turns this expression into an action, because it says this active here on the left-hand side of the prime is actually not this active here, but it's the active in the next state of the computation. So at this point in the computation, active I is true. This is the unprimed active, and then the primed active I is this active over here in the next state, and this is false. And this is where we can write active I equals true and active I prime equals false. If I would remove the prime here, clearly such a formula couldn't be true, right? Something cannot be true and false simultaneously. But because I prime it, we are actually talking about two separate states. The current state, active true, and the successor state, active false. And this guy down here has now to be updated to pending, because the only other variable in our system is the pending variable, and we're not going to touch pending in the terminate action. Right? Okay. So this is what defines the terminate action, and we are guaranteed for this terminate action this formula here to not execute concurrently with a send message action or with a wake up action it's really it happens atomically in our state machine that we've defined. Okay, questions so far? Please just speak up. Starting to wonder if my earphones turned off.
Okay, Markus, can you hear me?
Yeah, I can hear you.
Yeah, you noticed that we have explicitly noticed which variables not change, but in active we changed only one element of array. Should we also put here that other elements of array are not changed?
Perfect, perfect. Before I answer the question, let's give me an explanation. I will deliberately make a number of mistakes that a seasoned TLA plus user wouldn't do. But I want you to really understand the problem, understand the language by observing me doing beginner mistakes. And what you said is completely right. Here we don't define the value of active, we just define the value of active I. What happens to the other values of active? We don't know. So let's move to the next commit. See, it's this pending that remains. But active I actually has to be defined this way. And this here, the active except the ith element is false, is just syntactic sugar for simply defining active again in node and map it to if I equals n, then false, else active I. Yeah, because this is a little bit more, it can be written a little bit more compactly with the except. We have this except syntax. But now we fully define what the value of active is in the next state for all the values of I. TLA plus is untyped. Active in the next state could have been 42. In the previous state, in the current state, active is this function with domain nodes mapping to some Boolean value. But nothing stops us from saying that active in the next state is 42. It's no longer a function. It's this value 42. In the logic, both of them are sets, and they can't really be compared because it's silly to compare sets that cannot be compared. But it's a legal statement here. Usually we don't write specifications where the values of the variables change types because this makes it difficult for the human. But sometimes it's useful, right? Initially, it might be that some variable gets assigned some magic null value that we define someplace else. And then in successor states, it gets different types of values. But it's important, and this is completely right, we have to say not just what we change, we have to specify exactly what we change and also note what we don't change. This happens here with the except for this function. Great question. Okay, next step. Now we can do send message and pending. We can send a message, a node can send a message if it's active. It's like terminating of a node can only happen if it's active. Send message can happen if the node is active. And then we change pending this time, pending prime, except that we don't change pending of I, but of j, right? We send a message to some node j, and we increment its counter. And here's a little bit of new syntax, the add. The add just represents the value of pending j in the current state. This is what's the value of this add. And this add really just exists inside of this except expression here. So what this says is pending gets incremented for j by 1. And we leave active unchanged. Okay, and now for the final action, the pending action, the wake up action. So wake up, when can wake up happen for a node? Well, a node wakes up if there's a pending message. pending grade I greater than zero. We flip active back to true, familiar syntax, and then we consume the message, decrement the number of pending messages. And this, there's a question. There's too much chat going on. I would prefer if you just talk to me, because I can't keep track of all these chat questions. I think the last one is y minus 2. Good question. Again, a deliberate mistake we're going to catch later. Well, it should obviously be -1 here. But this is just this innocent typo that we made, right? Off by 1 arrow. They happen frequently. Now, later I will show how you can quickly catch these minor mistakes, even in a formalism that's untyped. And for now, we will just leave it in, okay? We'll revisit it later. So let's move to the next step. So we now have our 3 actions. We have our initial predicate that defines what the initial states look like at the beginning. So there's another question: shouldn't the action here, should this be an I instead of a J? Well, it's the node I that sends a message to J. And that means that there's one message pending at node J. I is active and it sends a message to J. The next question, one of the upcoming questions is it allowed for I and J to be the same? But we, so far, and this is what happens now as the next chapter in this tutorial, we're going to define where the I's and the J's come from. Because in some programming language, this might be it, right? I read about Redux in the chat, and I really don't know Redux, but now you could think there's some kind of magic framework that takes your actions and then executes the system and invokes these actions here. That's not true for TLA+. In TLA+, we have to define what happens in the next state by giving it a next state formula, a next state relation that takes the state and defines the set of successor states. Commonly, this is called next. And I've written a prototype of the next state relation down here. We could terminate with node 0, we can terminate with node I, we can terminate with node 2, terminate with node 3, and so on and so on. And it's written in a way that's obviously independent of n, and we're going to change that soon. We don't know yet how to make it, how to range over the elements and nodes. But this is what defines our system, right? And we can try and model check it now. So there's also this config file here. That's just for the tool. It's not really interesting. It says, okay, constant n is 4. We have 4 nodes. The init predicate is init, and the next state relation is next, with this keyword here, init and next. But this is really just configuration for some of the tools. This is not TLA+. So let's focus on the specification. Okay, in wake up or send message, does the order for the conjuncts matter? Could it be active after pending? The answer is, this is a formula. In math, order doesn't matter, right? We could just reorder this, move this to the bottom. The enablement condition doesn't have to come before we update, prime the variables, write the formulas for the prime variables. This is all equivalent at the level of TLA+. Well, some of the tools might not be able to evaluate this, right? We are writing math, and evaluating math is super difficult. We get all these kinds of liberties. We have all these kinds of liberties in math, and the tools just support a subset of it. And the tools then will give you useful error messages that say, yeah, you're trying to update the pending in the next state, and I don't know what the pending in this state is. These kinds of error messages. You will get the hang of it, how the tools work when you practice TLA Plus some more. But at TLA Plus, independently of the tools, the order doesn't matter. It's just a formula. And a conjunct list, the order doesn't matter. Also not in the disjunct list. So also down here, it doesn't matter at what line where we move this to. This just gets evaluated. There's no evaluation really going on. TLA Plus doesn't really have evaluation in that sense. Okay, but we wanted to check the specification with a model checker, check model with TLC. And let's see what happens. We give it, we don't want to check for deadlocks. And yeah, we checked our model. We didn't check anything useful about it yet, because we're still learning TLA Plus. But we get a success notification. It took a second, but something isn't right here because there's really just one state. That's a bummer. Why is there just one state? It's probably the initial state we've defined. Active and pending, true, everything's true, and 0 pending messages. But there is no termination going on, no send message going on, no wake up going on. Well, this is because of how we stated the next state relation. Because as I said, this is just math, right? So terminate 0, if we think this through, this evaluates to true. Let me make this smaller here. This evaluates to true if active 0 is true and active prime equals active, except for the 0th element, which is false. And we want terminate 2 to also be true. And simultaneously, that means active 2 is true. Well, that's actually the case here. But active prime means that active is the active from the old state, except that the second element in active is false. And this contradicts each other, right? So it cannot be that in the same state, active 0 is true, is false in the next state, and active 2 is false, when both require that all the other values don't change. So this formula simply is false, this next state formula down here, the way we've written it. Obviously, silly mistake. Let's correct this mistake. I'm going to skip 2 commits and make this smaller. So what have I done? I simply turned the and into an or. And now the formula can become true because this terminate 0 can be true while this is false, while this is false, while this is false. Perhaps this is true again. And let's see if we now get a couple of states. So now we have 16 states. We can also look at those states. Check model, and then we dump the output to some ATD file here. And we get this state graph here. As you can see, it already gets pretty large, even with just 16 states. But we see, okay, we have our pending here. Gray is the initial state. Everything's 0, everything's true. All nodes active, no messages pending. Then there's one state. This is a terminate action. Here it becomes false. There's another terminate action here. It becomes false. It goes from here. It can go from here to this state where false, false, false. So there's just one node that remains active. And here in the bottom state, all the nodes are false, all the nodes are inactive, and there are 0 messages pending. There is no send message going on because, right, it's not part of this next state relation here because I was omitted the rest of the next state relation. because we don't want to write this with explicit values. We want to make this work for the n in the constant, right? And this is what happened now. So now we say, okay, we have our set of nodes here. Give me two values from this set of nodes. Let's call them I and j. And there exists an I and j such that there is either a terminate I, a wake up I, a send message I, or comma j. Send a message from I to j. And now the question comes up, is it okay to send a message from node I to node j if I and j is the same? Can a node send a message to itself? Yeah, I guess it's fine. It's a modeling decision, right? Do we want to allow this? Do we want to disallow it? We could also disallow it. And then we say, write it like this. Okay, and now we can run this model. How many states does it have? Oh, oops. Already 80,000 distinct states, and it's not stopping. What's going on? Anybody wants to venture a guess what's going on here?
Maybe messages are accumulated and never delivered to the nodes.
Exactly. So conceptually, what you said is absolutely right. We keep sending messages, one node or a number of nodes just keep sending messages to some other node, and the receivers never receive those messages. This translates into pending being incremented, right, forever. And this model checker, it's just a finite state model checker, so we'll just keep generating states if it's possible to generate states. And it's for the natural numbers, it's always possible to generate a state where we increment the natural numbers. Now, so this will run until the end of the universe. Even though we constrained the number of nodes to a finite number, we still ended up with an infinite model. Because send and wake up or send could just happen indefinitely. So what we could do is we could just change our specification and write pending. The number of pending messages at I has to be less than 3. Oh, sorry, at j, obviously, at j. So don't send another message to this node if it's already overwhelmed. And then we get a finite model again. Great, 10,000 states. But this looks wrong, right? For somebody who doesn't know why we added this to our specification, they would just scratch their head and wonder, why can I only send 2 messages to J? Why can't I send 10 messages to J? And because this is just a limitation of the tool, right? This is not something that happens in termination detection in the algorithm. This is not something in TLA plus. This is some problem of the model checker. So what we want to do here, and I have to fast forward, is to create a model spec. This is common practice in TLA plus. So it's just another file that extends our previous file, and the config file is now changed accordingly. And in this file, I can define something that's called a constraint, which essentially tells the model checker, if you happen to encounter a state where this state constraint evaluates to true, well, then don't bother with the state anymore. Don't waste your time on it. Don't waste your breath on it. And right now it's true, so not much is going to happen. Instead, we write for all n in nodes, the pending n is smaller than 3 again, right? And assuming everything else checks out, it's wired up here. This should be a finite model now. I think it's a little bit larger, the model, because the n is 6. We can always observe the first part, the first stages of state space explosion. There's the question how to run the model checker. So you get this command prompt in VS Code. It's Control-Shift-P. And then you can type TLA plus, get all the TLA plus related commands, and check model with TLC. Get this other prompt where I tend to enter minus deadlock so that we don't check deadlocks with TLC. More on that later. And then it runs the model checker. Okay, now it completed for N6, and with this state constraint, we are at approximately 300,000 states, a diameter of 19. So that means that the depth of this graph is 19 levels, 19 steps in this graph. And the model checker generated 14 million states to evaluate the spec, but only 260,000 of them are unique, distinct states. Now you see there's this problem of state space explosion going on. This is generally a problem with model checking. Explicit state model checker, finite state model checker suffers from it a little bit more than the symbolic model checker. We can later also look at the symbolic model checker. But the fundamental question really is, why model check if there's a state space explosion going on? Our real implementation won't consist of, or a real system won't consist out of 6 nodes. It might consist out of 20 nodes, and they might send thousands and thousands of messages. But here we just check this for tiny, tiny values. N3, N5, at max send 2 messages, right? Why is there any chance in catching interesting bugs with these tiny values? The underlying hypothesis is that there's a thing called small scope hypothesis,
Markus,
that says even with tiny values, you catch bugs. They manifest, distributed system bugs manifest in, I think I got,
Markus,
1
wait
second.
a second. Markus, I need to interrupt you.
Okay.
A small warning. We are going to a small break.
Okay.
In a half a minute. So.
Yeah, let me just finish the sentence and then we can go into the break. Okay,
please,
great.
10 seconds.
So small scope hypothesis says you catch issues even with tiny values.
Oh,
N
Markus,
equals
I'm sorry.
3.
We can't finish. We need to back to it after the break. Don't switch back. We'll continue after a short break.